today we're going to start section 12.1. We're looking at vector valued functions. So we're first going to look at what it means to be a vector valued function. So a vector valued function is an equation, a vector equation R of t, which is f of ti plus g of tj plus h of tk, where f, g, and h are real valued functions of the parameter t. So how does this differ from what we've done before? Well, before, where we had f, g, and h, we had just numbers. They were constants, right? Now we've got functions that are playing into what's happening in the I direction, the j direction, and the k direction. Okay? But much of the things that you expect to be true are going to work. So take a look at the first example. We're going to look at domain. Finding domain for a vector valued function is just like finding the domain for any function you've ever done, right? You have things where you have to be concerned, denominators, radicals, stuff like that. And then there's places where you don't have to be concerned. So taking a look at the three functions, because that's what we have here. We have three functions, here, here, and here. Which ones have issues with the domain? So I has a domain issue. Just I. Why does J not have a domain issue?
Because it's defined for all.
Yeah, it's defined for all T, right? It has range, there's some range issues, perhaps. But there's no, not issues necessarily, but some restrictions. But there's no domain restrictions. So the only piece here who has a domain restriction is I. So this domain restriction, what has to be true about the 4 minus t squared? It cannot be less than 0, so it has to be greater than or equal to 0. Now, it may have been a while since you've solved an inequality like this. You cannot just move the 4 and take the square root. It doesn't work like that because it's squared. Now, if this were linear, you could just shift it around and solve it, and it would be fine. But because this is squared, you do this in Calc 1. So those of you who had Calc 1 with me, I know you did it. I know you all did it. But we have to factor it. So this factors as 2 minus t and 2 plus t. We want this to be greater than or equal to 0. These values, what we do is we set them equal to 0 to find what we would have called back then critical numbers for what we were doing it with anyway. Right, we're looking for things to be increasing and decreasing. This is domain questions. But taking a look at this, what values does this give me for t? 2 and negative 2. And then we would make a sign chart. The sign chart has those values on there in the correct order, of course. And we test a point in between everything, right, in each of those intervals. So if I test a point on the interval from negative infinity to negative 2, what point might you want to test?
Negative 4.
Okay, negative 4. We'll do 0 in between, okay? And how about after 2? 3. Awesome. Okay, so what do I test these in? Well, I test them into any version of it, but we might as well put it in right here. And I'm trying to figure out, is it positive or negative? And it doesn't matter what point I picked in each interval, I'll get the same sign. I won't get the same value, but I'll get the same sign. So if I put in negative 4, do I get a positive or a negative?
You get 0. Negative.
I get negative. You're thinking about putting in 2, not 4.
Oh.
Yep. Okay, so I get negative. If I put 0 in, I get a positive. And if I put 3 in, I get a negative. Which values are the ones that I want or am allowed to have?
Positive.
The positive values. So this piece right here is the part that answers the question greater than or equal to 0. So what that tells me is that my domain is exactly negative 2 to 2. Now let's just play around with this for a minute and ask the question. What if I had, like this, 2 to negative 2, but instead of having 6t here, I actually had t over, I didn't write that right, 6 over t here. What would that cause a problem with? 0. T could not be 0. So it would affect my domain down here, right? I have to have a domain that works for all 3 functions at the same time. Now this isn't a great example for showing this, but if I add this additional one in here and change the z up a little bit, right? There are the f of, what do I call it? 6t, the 6t up, the k component up a little bit. You can see what we'd have to do, right? we'd have to do an interval that would look something like this. -2 to 0, union 0 to 2. Make sense? So you need something that's restrictive to all three pieces. It includes all the domains for all three pieces and nothing else.
This might be a basic, like a basic question. I'm just not remembering. Why can't we include -2 and 2 in the domain?
We can. That's why the brackets are there.
Wait.
The brackets means that we include them, and if
Yeah.
they were parentheses, we wouldn't.
Oh, I was just flipping it around in my head.
That's okay, and that's why I put parentheses up here on the zeros when I gave my other example.
That makes sense.
Yep. Okay, and everybody's good on why we're including the -2 and the 2? Okay, wonderful. Okay, we're going to evaluate. Okay, it just means we evaluate all three pieces, right? So in this case, we actually only have two components. We only have an I and a j. That's fine. We're going to evaluate at the I and the j. So this is cosine of 0, I, plus 2 sine of 0, j. Okay, so what's the cosine of 0? 1. So this is 1 or just I. And what's the sine of 0? 0. So this last component disappears. If you want to write it right now for the moment, you can write that it's 0j. That's fine. But the answer to this is that this is the vector I. Pi over 4, a bit more interesting. We have cosine of pi over 4, I, plus 2 sine of pi over 4, j. So, I'll write it below, I've got space. What is the cosine of pi over 4? Close. Yeah, square root 2 over 2. How about the sine of pi over 4? Yep, and I have it multiplied by the 2 that's in front. So it's just square root 2. So we have square root 2 over 2i plus square root 2j. Make sense? Okay, so everything we're doing that worked for functions in, college algebra or, algebra 2 in high school or something like that, it's going to work because these inputs, right, the vectors themselves have the component that has three functions. So everything that we did for functions is going to work inside of vector-valued functions. All right, number 3. This is the place where we get to sketch something. We're going to sketch a curve represented by the vector-valued function and give the orientation of the curve. Okay, there's not a lot of questions that ask you to sketch or to give orientation, but I wanted to show you this one because it's kind of fun. So if you take a look at this, we have 3 components, right? So we have the component in the I direction, or we would sometimes call it x. This is like x is equal to 2 cosine of t. We have our y component. This is y is equal to sine of t. And we have our z component, and this is 3t. So the z component is what's happening as the t value increases along the z-axis, and it's just increasing linearly. So whatever is happening in the xy plane, it's just moving up at a constant rate in the z-plane, right? Because 3 times t would be a constant function that's linear. So I'd like to figure out what's happening in my xy plane. If I didn't have the z, what would this look like? Well, it's something we've seen before. So I'd like for us to take these two, and I'd like for us to remember that we have a lovely, because this is sine and cosine, we have a lovely relationship between sine and cosine that can come into play and be very helpful. It's called the Pythagorean theorem. So the cosine squared, I should have written it as sine squared just because we normally write it that way. Sine squared of t plus the cosine squared of t is equal to 1, correct? So let's actually take and change this like parametric wise, right? Let's change these back into what they are in terms of x and y. So in other words, I'd like to eliminate the parameter t. So sine of t, that's actually coming from over here, right? So this piece right here, if I were to square it, what would I get on the other side? Right? If I square sine, I get
Minus cosine squared.
just the sine t part,
Y squared.
y squared. Okay, so I'm just wanting to do a substitution. I'm taking this, and I don't really need to solve for sine t because it's already solved for sine t, but I'm going to square both sides. So sine squared of t is the same as y squared. I have to work a little bit harder on the other one because it doesn't say cosine of t, but it's not like a lot harder. What would I do if I solved this and I squared both sides? So it says cosine squared of t. What is it equal to?
X squared over 4.
Right. This is x squared over 4. We've seen this equation before. What is this an equation of?
Circle.
Close. You guys are close. You're thinking three-dimensional. So if you've said sphere and ellipsoid, you're thinking three-dimensional. We're just doing or 2 dimensions. It's not a circle. Somebody said fine. It's an ellipse. Why is it not a circle?
Because they're not the same radius.
They don't have the same radius, right? Like, in other words, the coefficient in front of the sine squared and cosine squared, or the denominator underneath the x squared and the y squared don't match. Everybody with me?
Yeah.
Okay, so that was the distinguishing factor between an ellipse and a circle, is that when circles are present, we would actually have this saying y squared plus x squared equal 1. Here we have x squared over 4. So if I were to draw this in 2 dimensions, and we can do that pretty quickly, and we can do this in terms of t if you wish to, but if you were to do this with t, for example, so let's just go back up to the original equation and isolating the x and the y variables. Because it's sine and cosine, it works really nicely to do like pi half values, so like 0, pi over 2, pi. I think that's probably enough to show what we're doing in the x and y. So if I put in 0 for x, I have 2 cosine of 0. That would be 2. And if I put in 0 for y as the sine t, so sine of 0, I would get 0. If I put in pi over 2, and I'm putting these in right here. I'm looking at it, but I haven't marked it. This is where I'm putting them in. So all right, sorry, there we go. So if I put in my, or you can say I'm putting them in here if you prefer, that's fine too. So pi over 2, so 2 cosine pi over 2 would be, what's cosine pi over 2? 0, so times 2 would be 0. And then sine of pi over 2, 1. And then if I put in pi, cosine of pi, negative 1, which times my 2 would be negative 2, yeah. And then sine of pi, 0. So if I were to start graphing this in 2 dimensions, the graph will actually look like, from a parametric point anyway, these ordered pairs. So x is 2, y is 0, right here. X is 0, y is 1. And then I flip over to the negative side. And if I went one further, it would be down here. And so these are going to be that ellipse that you're expecting. From the standpoint of the rectangular coordinate equation that I did, right? Y squared plus x squared over 4 equals 1. We can think of it from that way too. The number underneath the y tells us how far away from, well, the center is 0, 0, right? Because I don't have any pluses or minuses with the y's and x's. So I've got 0, 0 as my center, and then the number underneath y, 1, tells me how far up and down I go. The number underneath x, square rooted, tells me how far left and right I go. So I'm going to 2. This is an ellipse, okay? But it's an ellipse that gets traced. But as it gets traced, it's increasing in terms of t, right? And in terms of z. What am I getting?
Spiral.
A spiral. Okay, it's got a spiral, but it's not a spiral that's like a slinky, right? Right? It's not a circular spiral that's going up. It's an elliptical spiral that's going up, right? So imagine when the slinkies get squished, they don't slinky very well. But if you had a coil that did that, right, it would be an elongated coil, not a circular coil. So how do we get to draw that in 3 dimensions? Because that's actually what we're trying to do. We haven't answered the orientation question. Don't let me forget that, okay? So this one is x, and this one is y, and here's my z. So we are starting on the x-axis at 2, so I'm going to be over here. And from here, I am spiraling up. And it's doing it in an elliptical way, but it's really difficult to draw the elliptical part of it. But it's not too bad to draw the fact that it's spiraling. And you can certainly make more spiral loops in there and make it more condensed if you'd like. It looks something like this. Now, it's fine to talk about the orientation in terms of the spiral, but it might be easier to think about it in terms of 2 dimensions. So let's do it from the 2-dimensional perspective first. Which direction, and by direction I mean clockwise or counterclockwise, that's what orientation is talking about. Which direction is it going? It is going counterclockwise. We've moved in this direction as we plotted our points. And if you take a look, the same thing happened with my spiral. I moved in this direction, right? So this orientation is counterclockwise.
Do you want us to draw the arrows and say what direction?
No, as long as you've written the counterclockwise, you don't have to. I just wanted you to have a visual to see it. Okay, what do you think? It's okay?
My drawing's pretty bad.
Your drawing's bad, I'm sorry. Okay. Let's take a look at another one. So if we've taken something and sort of parsed it out and looked at it in terms of a rectangular equation, which is what we've done here, right? We should be able to go back the other way as well. So now we actually have a rectangular type equation, right? It says x squared plus y squared equals plus z squared equals 4, x plus z equals 2, and x equals 1 plus sine t. And we're going to create a vector valued function with those details, okay? So we need to merge some of these equations together, and we need to introduce, if you will, a parametric or a parameter t. All right, so one of the things that we can do pretty nicely is with the last 2 equations, not the squared equation so much, but the last 2 equations, is that it's fairly easy to do a substitution. Make sense? So I've got x plus z equals 2, and I've got x is equal to 1 plus sine t. So this is the one that's already got the parameter in it, and so this one is going to come and it's going to merge to being substituted inside of the second equation. So I have 1 plus sine t, and then I have plus z equals 2. Okay, I think I got it in there, right? And the goal is to solve this for z so that we have z in terms of t, right? We want to eliminate the parameter or eliminate the variable x. So I can move my values to the other side. What will z equal?
1 minus sine t.
Okay, so I have 1 minus sine of t. Is everybody good at that?
Where did that come from?
We just shifted things, right? We subtracted 1. There's my 1. We subtract the sine t.
Oh, okay.
We're just solving. Okay, so we have our z and we have our x. And we really need a y. Right? I need an x component, a y component, and a z component. Those will be the f, the g, the h that go beside the I, the j, the k, in our vector valued function equation. So we need to figure out what y is. Well, I know what x is in terms of t. It's the first box. It's 1 plus sine t. So I can put that in terms of the x squared. I can read the replacement there. I know what z is. It's 1 minus sine t. So I can put that in terms or in the place of the z. So I'm going to do another substitution. It's just not as nice of a substitution as the last one. It's a little trickier to do, just messier. So we're going to have 1 plus sine t squared, because that's what x is. Plus y squared is the one that we're actually going to be solving for. Well, y is in a minute. Plus, and then z is 1 minus the sine of t, and then it's squared, and it's going to equal 4. Okay, so we're going to do some simplification, some algebra simplification. So please remember, we do have to FOIL or distribute things out. Don't just square independent pieces. So if I distribute this out, I'm going to have a 1 plus perfect square trinomials means I can multiply the 1 and the sine t together. That would give me sine t and then double it. This is 2 sine of t. And I can square the last piece, plus sine squared of t. I have my y squared, and I'll do the same thing with the 1 minus sine t squared. So I have a 1 squared, which is 1. I'll have a minus 2 sine of t. And then I'll have a plus sine squared of t, and it equals 4. So I'm going to combine like terms. Tell me something you see that can combine nicely.
2 sine of t, just cancel it.
Yep, those are gonna cancel. That's the nicest one. What else is gonna combine?
2 sine squared of t.
Yep, so this one and this one are gonna give me 2 of those. So I have 2 sine squared of t.
You can add the ones and subtract them.
Okay, so I have a 1 here and a 1 here. That's 2, and I can subtract it to the other side. So 4 minus 2 would be 2. So I can shift that over. If you're good to do it all together, I'm good with that. I think that just leaves y squared, doesn't it?
Yep.
Okay. And so we're going to shift that to the other side. So I have y squared is equal to 2 minus 2 sine squared of t. You might look at that and say, well, I'm just going to square root it and I'm going to be done. But there's actually one more theorem that you can use to make this simpler. Do you see it?
Oh,
You can use the one from the last one,
Which is, do you remember what it's called?
the Pythagorean theorem.
Yeah, Pythagorean identity can be used here, right? So what do I see by saying that? Well, I didn't write it this way, but we can actually manipulate a little bit. So I have sine squared of t minus or plus cosine squared of t is equal to 1. But if I shift the sign to the other side, the cosine squared of t is actually equal to 1 minus the sine squared of t. Now, I don't have 1 minus sine squared of t. I have 2 minus 2 sine squared of t, but that's okay. I can just factor a 2 out, and then I do. So let me see if I can get this a little bit smaller for us. All right, I'll change that in a second. All right, so we can rewrite this as pulling a 2 out, and then we would have 1 minus sine squared of t, which is going to be cosine squared of t. And of course, the reason that that's nice is because I can square root it and I can actually simplify it now. Now, I can't simplify the square root of 2. It's going to be square root of 2. But the other piece would just be cosine of t. So this is my y value down here. I had my x and my z value above. So if I'm writing my vector valued function now, I'll write it here at the bottom. We'll see if I have enough space. It's r of t equals, and I write the x component in first. That's the one I was given. It's 1 plus sine of t I. I'll write in my y component. That's what I got here at the end, which is the square root of 2 cosine t j. And then I have my z component, which I found above as well, to be 1 minus sine of t. Okay. Do remember your hats on your j's and k's. Remember your parentheses around the 1 minus sign and the 1 plus sign, those pieces, so that we don't lose the distribution, yeah.
So you want it in an equation form and not in the vectors?
Correct, yeah. They're going to have you put it into an equation form. So, yeah. That's what a vector value function by definition is going to be. So that's why we're going to write it that way. Okay?
Okay.
Yep. Okay. Ready to look at limits? Somebody said limits when I saw this already coming in today. So we're going to look at limits. Just like everything else, though, they're going to behave the way that we would expect them to, right? So if we have our vector valued function, f of ti plus g of tj plus h of tk, and we want the limit of that function as t approaches a, we just take the limit of each of the individual 3 functions as x approaches that value, as t approaches that value, excuse me.
on the underlying part with limit of g of t, is that supposed to be a j instead of a k?
Yes, thank you. Can't erase. Wow. That should be a J. Yes, thank you, Noah. My Calc 3 students next fall are going to be so happy that you guys found all my mistakes. They're not even going to know. I know. They should be so happy though, right? Those are my Calc 1 students now, so they're going to be with me for 3 semesters, those who have to go as far as you guys have gone so far. Isn't that crazy? Yeah, isn't that crazy? All right. We're good? Do you have it all down? Great. Continuity is next. And again, it's just an analogous continuity statement from Calc 1. So if the limit, if it's continuous, or it is continuous, I should say, it is continuous when these 3 things hold. Number 1, the limit exists. Number 2, the function value exists. And number 3, the limit and the function value are equal to one another. This is the exact same statement, but with different notation from Calc 1. Okay, does everybody have it? All right, so we're going to do one question with limits, and then we're going to do one question about continuity. So this is another form that we could write in besides the equation form, so it's component form. That may have been what you were asking about, and I wasn't quite understanding. So we can have component form with functions inside of the components, just like we had component form with numbers inside of them. That's perfectly acceptable as well if you prefer to do that on a particular problem. So if we're wanting to find the limit of this component form vector valued equation, we just find the limit of each piece, right? So we'll take the limit as t approaches 0 of the sine of t over t. And we'll take the limit as t approaches 0 of the cosine of t. And we will take the limit as t approaches 0 of t plus 1 over t minus 1. Now, the first one is one of the cases where you can't just put it in, right? If you try to just put 0 into sine t over t, you're going to get 0 over 0, right? So this is a special limit property that we encountered in Calc 1. Does anybody remember what this limit is? I have 2 people's hands. It's 1. Agree, Noah? Yeah, it's 1. The 2 limit properties, if you flip back in your book to that point, you'll find is the limit, as I'm going to do it in terms of the way it writes it, as x approaches 0 of sine of x over x is 1. And then there's a similar one for cosine. And so you can check that one out too if it comes up. But that's the one that we're using here. And so this is going to be the number 1. The second one, though, you can actually evaluate it, right? You can actually put the 0 in. So what is the limit value for cosine of t as t approaches 0? That one's 1 as well. And then how about the limit as t approaches 0 of t plus 1 over t minus 1? That one's negative 1. Now, notice, if they had given you something here, like let's say that they did t approaches 1 instead of t approaches 0. So this 1 at the end, you couldn't do it, right? What would that mean? It means the limit doesn't exist. It doesn't exist for the whole vector value function because it didn't exist for each of the 3 components. All right? Kind of like one of those domain issue kind of things. It's got to be present for all of them or it doesn't count.
And isn't the sine t over t, isn't that just L'Hopital's rule and you just get cosine t?
So L'Hopital's rule is actually proven later than that is introduced. And so there's other justification for that if you take a look back in, I think it's in chapter 2. That sounds right. So, but you can see L'Hopital's rule can certainly show that it's the same result. But we do it far before you do L'Hopital's rule.
So we can use L'Hopital's to find stuff like that, though?
You can. You can think about it from that perspective. Yeah, that's not a problem. Yeah. Okay. It's kind of like we did limits and stuff back in chapter 9, your favorite chapter, right? Yeah, exactly. It's the same thing. We did L'Hopital's rule there too, didn't we, Noah? Yeah, we did.
Their favorite chapter.
I think it's a lot of fun. All right.
It's just such
introduction.
It's a big introduction. All right, 6, our last one for today. We are going to determine the intervals on which our vector valued function written here is continuous. So this is kind of like our first question of the day, which was about domain, right? We need to figure out where it's continuous on each individual interval. And then we need to figure out, when we look at all of those, what's the adjoining values that it works for everything, just like domain. So taking a look at the cosine of 5t, where is this continuous? Yeah, so this one is continuous everywhere. So I'll write it the way you said it, continuous from negative infinity to infinity. How about tangent?
Negative pi over 2, pi over 2.
So is that the only place though, Alex?
No, any interval that integer.
Yeah, so y'all remember the graph of tangent? And it's got this sort of cyclic nature to it, but it has asymptotes at every odd pi over 2 value, right? Odd pi over 2. I think I'm saying it the way that I mean to say it. So this one's continuous, but it's continuous as long as the t value is not equal, and it's not pi over 2, it's pi over 4 is what I meant to say.
Okay.
Yeah, pi over 4. It's continuous whenever the pi over 4 plus k pi is not happening. So the plus k pi gets us every interval after it. That's one of those ways they're writing it. Depending on where you took trig, you may or may not have seen that. We definitely do it in our trig course here. This k value is an integer, so we'll say k is an element of the integers. So it's continuous everywhere except those places. Right, so it's continuous from negative pi over 4 to pi over 4, and then from pi over 4 to 3 pi over 4, 3 pi over 4 to 5 pi over 4, and so forth.
What's that last thing you drew at the end of the?
Z
K is an element of z. Is that what you're talking about?
Yeah.
Z is an integer.
Z is the integers.
Okay.
This is integers. Where do you guys see that? Did you see it as discrete?
Yeah.
Okay. All right, we teach it in a variety of different courses. If you've taken a modern or a linear algebra course, you've probably saw it in there too. Some of those notations, the integer symbol, the natural number symbol, and so forth. It just means integers.
Yeah, it was
If I'm remembering right, y'all can tell me if I'm remembering right. I think it's Latin. I think the Z comes from the Latin. Most of the other ones are the variable or the letter that they're starting. Like real numbers is R.
Yeah.
Rational numbers is Q because Q stands for quotient, fractional, stuff like that. But this one's integers. Okay, last one, or last piece of this. ln t. Where is this one continuous?
0 to infinity.
It's continuous from 0 to infinity. Okay? So these three are all different continuity restraints. The first one being the most amiable to everybody else. You don't really have to do anything with him. We really just need to make amends for the fact that the last two are different. So I need to make sure that when I describe my continuity, I exclude the right things and I include the right things. So how do I do that? Well, I actually have to write it out in a pretty convoluted way. This is continuous for all t greater than 0. Y'all know that notation? Okay. Now you've got me a little skittish. For all t greater than 0, when t is not equal to pi over 4 plus k pi for integers of k. That's some good math writing for the day. Okay, there's no way to write that in an interval, right? Because you have unlimited, infinite, if you will, intervals that this is talking about, right? So it would go from 0, not included 0, to pi over 4. And then from pi over 4 to 3 pi over 4, and 3 pi over 4 to 5 pi over 4. The only thing that got left out is all the negative side of the graph because of the second, or because of the third one with the natural log. Okay, makes sense? All right.